We're going to talk a bit more about the kinetics of chemical reactions today. And to start with, we're going to talk about the law of conservation energy yet again. We said in the past that energy cannot be created or destroyed in the course of a regular chemical reaction. What it can do is change. So you've heard the terms potential and kinetic energy, and I'm going to sort of give them a little different definition probably than what you've heard before, at least for potential. Potential energy, I'm sure you've heard as described as stored energy, and I agree with that. I just want to change it a little bit and call it the energy of position. And the reason why I say that is if you had a hill with a ball at the top versus a hill with a ball at the bottom, the reason why that ball at the top of the hill has more potential energy is because of its position. So it's not necessarily just stored, it's based on where it is. And that'll actually make more sense when we talk about phase change later on. And then kinetic energy is the energy of motion. So what I have here is a diagram of a water molecule. This would be an oxygen atom, and then these are the two hydrogen atoms. And the black lines actually represent shared electrons or bonds. So this is a bond between the oxygen and the hydrogen atom. And energy actually comes from the formation of bonds. So we're going to say it comes from bonds. Typically, the point in forming a bond is to make a more energy stable molecule. So in the formation of bonds, since they're becoming more stable, they lose energy. But like we said before, energy can't be created or destroyed. It changes form. That energy that's lost in the formation of those bonds actually becomes a different form of energy. Just a quick review, we've talked about electrolysis before. Electrolysis is, when we get more into bonding, you'll find out that water wouldn't conduct electricity on its own. I know that's kind of hard to understand because people tell you to get out of the pool if there's a thunderstorm. Well, guess what? The amount of electricity and lightning is so great that it could really make anything conduct electricity. It makes air conduct electricity, so that's sort of a special case scenario. Water is actually an incredibly poor conductor. So in order to do electrolysis of water, what we do is we put something in the water that does conduct electricity. And I'll do an example for you in class, but what we put in there is sulfuric acid. And sulfuric acid is a diprotic acid. It's pretty strong. And because the hydrogen ions dissociate from the sulfate ions, it becomes conductive. So electrolysis is using electricity, and when we talked about this before, we used electricity to isolate highly reactive metals or nonmetals. We talked about that's how we purify group 1 and 2 metals or group 17 nonmetals. This time, the example I'll do for you in class, we're actually going to use electricity to separate the bonds between hydrogen and oxygen and water. So let's talk about that reaction, and we're going to talk about that reaction in terms of a potential energy diagram. And a potential energy diagram shows what happens to potential energy in the course of a reaction. So here is the general structure for a potential energy diagram. Those dashed lines, they aren't really significant. We're going to use them so that everybody has the same type of diagram, but you're not always going to have lines in your diagram. This is a general trend. On the exam, you may actually see values associated with the y-axis, but for this, we're just going to do a general trend. So before we can actually fill in this diagram, we need to find the decomposition of water in table I. So I'm going to pull up my table I here, and we're going to find where we decompose water. And what you're going to find is that it's backwards, right? Maybe we should use this one because I'm going to start with liquid water, not gaseous water. So I'm going to have to write this backwards, and if you recall, when we write this backwards, then we have to change the sign on delta H. So let me kind of move this out of the way a little bit. And we're going to write this backwards. So I'm going to put my products as my reactants. So my 2 water in the liquid form becoming 2 hydrogen in the gaseous form plus oxygen also in the gaseous form. And then our value for delta H, we're going to use our same value. We're just going to change the sign. So it's going to be 571.6 kilojoules. Let me get that out of the way. So when we draw our potential energy diagram, if you recall when we talked about delta H before, delta H is approximately equivalent to potential energy, or at least whatever happens to delta H is what's happening to the potential energy. So we know in the course of this reaction, potential energy must be going up. So we're going to start low on our reactant side. So we're going to start down here. And then what will happen is it'll absorb a lot of energy in the course of the reaction. And what will happen is in the course of that reaction, you'll actually see a little hump before you get to the product side. Now there's a whole bunch of things you're going to have to be able to label and recognize in one of these potential energy diagrams. The first thing, this is like zero energy here. So from the zero energy to where we started from, that's going to be the potential energy of the reactants. That's where we're starting from. Our reactants have some energy to start with. They aren't zero, okay? They do have some potential energy. At the other end, from 0 to our products, that's going to be the potential energy of our products. And then probably the most important thing, the difference between those two, and I'm going to kind of offset this a little bit because I know we're drawing more arrows. The difference between those two is delta H, or the heat of the reaction. So if I had assigned values to those dashed lines, the difference between here and here would be that 571.6. That's the amount of potential energy gained through the reaction. Now, there's another line you need to know. From our starting point, or the potential energy of our reactants, to the top of the hill is where that reaction is going to actually occur. We need to have the proper orientation and the proper energy for those molecules to react with each other, or in this case, to dissociate from each other. And to do that, we have to get to the top of the hill. And we call that the activation energy. It's the energy required to activate our reactions. So this is the activation energy. Note that it does not start at the 0 line. It starts from where we're starting, or the reactant side. And then there's one more arrow you have to know, and it goes from 0 all the way to the top of the hill. And that line they call the activation complex. So that's the total energy in the system at the point where the reaction can occur. So this is the activation complex. Really important to note that where I've actually drawn these arrows isn't important. What's important is where I start from and where I go to. So I could theoretically draw any of these arrows at any point in my graph, and you would have to be able to identify it. So if I drew this right here, you would have to know that that is delta H, or the heat of the reaction. So even though it's not in the same position, it's going from the same starting and ending point. So you would have to be able to recognize that that's delta H. All right, we're going to do the opposite reaction now. So we're going to go from our hydrogen and our oxygen to our water. So this is actually how it was written in table I. So I'm going to put my 2H2 gas plus my O2 gas, and we're going to make 2H2O liquid, and my delta H is going to be negative 571.6 kilojoules. So this time we're going to lose energy. Since we know we're going to lose energy, and you'll see we're going to lose that energy in the form of heat. And that means we must be starting up higher, and we're going to have an activation energy again. So we're going to need to activate the reaction, and then we'll come down to our products. Now all the arrows are going to start and end in the same points, keeping in mind that this is the reverse reaction because we're actually going to be losing heat in this reaction. Delta H is negative, so the heat's going to be lost in the reaction. So starting from 0 to our reactants, notice it's a much higher arrow this time. This is the potential energy of our reactants. And then over here, from 0 to our products will be the potential energy of our products. The difference between those two, and I can draw this anywhere I like. In fact, I'm going to draw it over here because I didn't draw a very large graph here and I'm going to need more room, is delta H. The difference between the potential energy of the reactants and the products is always delta H. Then our activation energy would be from our reactants to the top of the hill. So this one, and I'm going to have to draw this off to the side, activation energy. So that's the energy required to go from our reactants to the top of our hill. That's the activation energy. And then one last thing here, that's the activation complex. The total energy in the system required for the reaction to occur. There's one more thing I want to point out here, and actually I won't be able to show this in our example in class, but you can actually lower that activation energy by adding some sort of catalyst. And usually we show it as a dashed line, so sometimes they'll ask about that, and your activation energy would actually be lowered. So again, starting from the potential energy of the reactants to the top of that shorter hill, we're going to call that the activation energy with catalyst. And we could have done that on the front side as well. And I suppose they could ask the activation complex with catalyst as well, and your arrowhead would just stop at the top of the dashed hill. So that would be activation complex with the catalyst. We need to discuss some factors that can affect the rate of a chemical reaction, and these are things you will need to memorize. So since we talked about how these molecules have to be in the proper orientation, have the proper energy, be hitting each other in the correct orientation, there's quite a few things that can affect the rate of this chemical reaction occurring. One of those would be increasing the concentration. So concentration can affect the rate of the reaction. Essentially, if you have more stuff, you're going to have more collisions. And that's really what matters, is those collisions. We call that the collision theory. The next thing that could change the rate or the amount of collisions is the temperature. Temperature is average kinetic energy. So essentially a snapshot of how fast molecules are moving. So the faster they're moving, the more collisions there would be. A lot of these are common sense. Something else that we were just discussing would be a catalyst. The sulfuric acid could actually be considered a catalyst because it allows the water to conduct electricity at a much lower amount of electricity. Like I said before, water will conduct electricity when you're putting a lot of voltage through it, like with a lightning bolt, but normally it's an incredibly poor conductor. So a catalyst will increase the rate because it lowers the activation energy. It lowers the amount of energy required for the reaction to actually occur. The next thing would be the nature of the reactants. And I have a couple of bullet points here to explain a little bit more about that. So your reactants and what their nature is can affect the rate of the reaction. So the first thing, and I think this will make a lot of sense to you, is that gases actually react faster than liquids. Gases have more space to move around and they're moving faster than the molecules in a liquid. So if your reactants are gases, they're going to react faster than if they were liquids. Likewise, liquids react faster than solids. In fact, solids are pretty inert typically, and if you wanted them to react, you'd typically either melt them or dissolve them to get them to do something. This last one, though, might not make a whole lot of sense to you, but it's only because we haven't finished discussing bond types, and that is that ionic compounds react faster than covalent. And ionic compounds are salts. And shortly we'll be talking about the difference between ionic and covalent, but essentially salts are when you have a metal bonded to a nonmetal, and covalents are when you have two nonmetals bonded to each other. Covalent compounds share their electrons, typically pretty close to equally, where in ionic compound, the metal actually will lose its electron to the nonmetal, and then the two are attracted to each other because of their charges, the metal being positive, the nonmetal being negative. So it's easier for those to dissociate from each other, especially when melted or dissolved, than with a covalent, because even if you could dissolve a covalent, the atoms don't dissociate from each other, where in ionic they do. The next one is the reaction mechanism, and by that I mean what has to happen in order for the reaction to occur. Sometimes multiple steps have to happen in order for the reaction to go to completion. So the simpler the reaction, the faster it'll happen. If there's multiple intermediate reactions, it's going to take a little longer. And then the last one we're going to talk about is something you've probably covered before in other courses, and that's surface area. You may have in the past done an experiment where you've dropped a sugar cube in water versus a spoonful of sugar. And you would find that the spoonful of sugar actually dissolves faster because there's more surface area to react with the water. Granted, that's just dissolving, but the same is true with chemical reactions. If there's more surface area, that means that there's more area for those collisions to occur. Therefore, the reaction will be faster. So we're going to say greater surface area, faster reaction. And that's the end of our notes.